In this video, I'm going to talk about a quick review on how to make an epoxide from an alkene and halohydrin. I'm not going to talk about the mechanism, but just a method of making an epoxide from an alkene and a halohydrin. And for the mechanism, we will see some other videos in the chapters of alkenes itself. To make an epoxide, obviously, first of all, make sure you know what an epoxide is. So epoxide would be where you have two carbons that are connected to the same oxygen atom. So it makes like a triangle there. And then I can have like, different R groups there or the same R groups. That could be something that you have to look into. Like you have the same side of carbon chains on the left or on the right, or it's a different one. Another one would have been something like I can have an oxygen here, so that's an epoxide as well. Now, one of the ways to make an epoxide is we use an alkene, and when we're using an alkene, we use something called an peroxy acid, or one of the common peroxy acid is used, that's an MCPBA, or they probably just say peroxy acid. Or another way of writing that would be RCO3H. So you could possibly be seeing any one of those as in the form of the reagent. They are same forms right here. So peroxy acids or RCO3H or the MCPBA, they're just the same thing. MCPBA is one example of the peroxy acids that's most commonly used. So what it really does is it just provides an oxygen. So like I said, if you want to look at it in a mechanism, we'll look at the mechanism of that when we look at the alkene chapter. So what really happens, it provides an oxygen, and that oxygen gets installed where you have that double bond in there. So that's really it. That's what we really got going on in there. And you could have this oxygen kind of added coming from the top or coming from the bottom technically. And when that happens, it would either have this either coming out of the page or going back in the page. Now, if you look at the last carbon here, that's not really chiral, so I'm only going to be worrying about this carbon being in the chiral center, so I can have that either coming out of the page, but then I can also have going back in the page, so I would make a pair of enantiomers. But now, what if you use something similar when you have a ring? So I'm going to go ahead and use MCPBA again. So when I use an MCPBA again, we're going to have the epoxide created here. And when we create the epoxide, you would either have this oxygen coming out of the page like this, or I would have another scenario where it would be going back in the page. Now, the question that you want to ask yourself, what is really the relation between those two? Now, we have said earlier in the previous case that, okay, well, we actually made a pair of enantiomers there, even though we have only one chiral center, but still having one chiral center, that means the other product would have that chirality flipped. But here, it kind of seems like it is going to be an enantiomer, but then remember, this molecule actually has an internal plane of symmetry. So there is an internal plane of symmetry. So as a result, this is not going to be the enantiomers, but they're rather going to be identicals. And why they're identical? Well, they are the mesos of one another. So that's why they're identical. So why we didn't call the previous one to be mesos, that's because there was no internal plane of symmetry on that. I mean, you can kind of see the line. If you draw one here, the left side of the molecule is not the same as the right side of the molecule. So that's something you got to be careful with. That's one way of making epoxide. The second way of making epoxide, if you have an halohydrin. Now, what is really an halohydrin and how you really make it, that's in a different story, but I'll just talk about that. I have an halohydrin, and I can actually start from this one. Like suppose I got this guy right there, and one of the ways of making an halohydrin is using an alkene, and you use some sort of halogen with water basically, and what you ended up making here is you would have in one carbon you would have the bromine installed, and in the other carbon you have the OH installed, and they're going to be anti to one another, so you can possibly make a pair of enantiomers here. So it's an anti-addition basically. So this reaction you would see in the addition reactions of alkenes. So I'm not going to talk about the mechanism here, but this is what really the halohydrin is. And I can go ahead and use this halohydrin. And you don't have to have an halohydrin only in the rings, but you can have it in an open chain as well. I'm going to go ahead and use an halohydrin here, and I'm going to go ahead and use a base here. So I'm going to go ahead and use, let's say, NaOH. So NaOH is not a really strong base when it comes down to the alcohols, but you will set up an equilibrium in the first step here, and that equilibrium would have a part of this oxygen deprotonated from the alcohol. So when you have a part of that, protons kind of removed here, you eventually get a negative charge on that oxygen here. All right, so I want to go ahead and get a negative charge on that oxygen. Now, all of a sudden, this oxygen is kind of right next door to this alkyl halide, technically, which is in a secondary alkyl halide. So I could go ahead and do a backside attack here, and this is really perfect in terms of orientation. So when I'm doing the backside attack from that oxygen, the oxygen has to come from behind, and it's like you can look at the bromine is kind of coming out of the page and the oxygen is going back in the page. So they're already opposite to one another. So it kind of makes in a perfect sense. So you can do in a backside attack here. So I'm going to go ahead and do in a backside attack here. And then your bromine is going to leave. So this is a typical SN2 reaction at this point. And what I'm going to get at the end of the day? Well, we're going to end up getting an epoxide here. Now, how this epoxide is going to be oriented? Well, it seems like this particular one will have this oxygen will be going back in the page. But even if you draw the one that's going to be coming out of the page, and since this has an internal plane of symmetry, it would still be the same compound. It's not going to have any difference in there. Well, I could have said that, okay, what if I'm using this same guy here? And I'm just going to copy this down here. So what I'm going to do is instead of having the bromine kind of coming out of the page, I'll have these flipped basically. So when I have these flipped, what I'm going to get is, let's say I'm going to have this coming out of the page. This bromine is flipped, still opposite to one another. So we are still going to be in the condition of doing the backside attack here, running an SN2 reaction. But the end of the day, the difference in the product is that this oxygen or epoxide is going to be coming out of the page. But then what we really see here is these guys are the same thing. They're identicals because they are the mesos of one another, and that's because you have the internal plane of symmetry in there, and one chiral center is going to be R and the other one is going to be S, and you can figure that out on your own. But it's not that you're always going to be making the same compounds or the mesos. What if you actually have a compound where you don't have an internal plane of symmetry, where suppose I'm looking at something like this here. Suppose I got some bromine here that's coming out of the page, and I have, well, this center is not, that there's an OH there. So if you look here, this is not really chiral center, so I can draw the OH however I want. But eventually, how you want to have the OH as, let me just draw this in this form for a minute. Okay, and then I have two hydrogens here. One is going out of the page, another one is coming back in the page. So what I want to do here, I will go ahead and use NaOH again. So run an acid-base reaction, and then the acid-base reaction, when it's ran, I will have this stuff made here, which is going to be the O minus. But then if you see here, the O minus is not really in that position where it can do the backside attack. For this O minus to do in a backside attack, it must be actually going back in the page. So what we really got going on here is the hydrogen that's back in the page. But I can easily get this oxygen back in the page because it's in a single bond and you can run a rotation around the single bond easily. So when you run the rotation around the single bond, so I'm just going to say, okay, I'm going to just go ahead and rotate it just so that I have these guys properly oriented to run in an SN2 reaction. And I have two hydrogens to be the same, so it doesn't really matter like which one you really move. One of them is going to be, really here. Let me just going to call this, let's say H1, H2. So when you're flipping it or when you're swapping it, everything gets swapped. So the H2 is going to be here, and H1 is going to be here, and then your oxygen is going to be going back in the page. So it doesn't really matter because it's not really a chiral center. I can easily get this oxygen back in the page. Now I can run an SN2 mechanism here very easily because it will be easy for him to do in a backside attack here, and the bromine would leave. So that's like an SN2 orientation. And then what I get at the end of the day, how you make the product here probably going to be important. And since this oxygen is going to be doing the backside attack here, and this is really the only chiral center you have, when you run the SN2 mechanism, you make sure you invert the stereochemistry at that particular chiral center. So I'm going to have this oxygen now going back in the page, and the other carbon oxygen is also going to be back in the page. But like I said, it's irrelevant for this right carbon because it's not really chiral. What's more important is how the orientation you're going to have on this carbon and needs to be flipped compared to what you started out with, because remember, SN2 involves an inversion in stereochemistry. Now, you have to worry about the stereochemistry only if there's a chiral center. And sometimes in the questions, they don't really ask you about the stereochemistry, but they just ask you how you can actually do this reaction or how you can obtain the epoxide. And if they don't ask you about the stereochemistry, you don't have to worry about the stereochemistry. Now, I do want to mention one more thing here. Now, some of you may be thinking that this OH minus that we were using and then we used earlier here to kind of do the acid-base reaction. But then remember, this is a strong nucleophile and a strong base. So why not this OH minus doing an SN2 reaction itself onto this carbon here? Well, the answer is simple here. Your acid-base reactions are a lot faster than your nucleophilic electrophilic reactions. So you would have a better shot of this being used to remove this proton. So, or another way of saying it will do that more quickly. So you will have this oxygen with a negative charge right next to this secondary alkyl halide, you can say, a lot faster. Now, as soon as you have this negative charge onto this oxygen, it kind of very similar in terms of its nucleophilic strength as that of an OH minus, but what really helps the reaction or formation of oxide here eventually is the proximity effect. The reason why this works better is because it's just right there, for this OH to kind of go in there to do the nucleophilic attack, it has to come from somewhere else. But when you look at this O minus here to do the nucleophilic attack, it's right there. So it's easier and it has a larger probability. So that's why it's going to be the major product, and you are not really going to be seeing this OH acting as a nucleophile and doing the nucleophilic attack here. Even if it does, it's going to be in a very small amount, but your major product is going to be the epoxide here.